So now let's actually look at the second imbalanced case. The second case, remember the previous case that we discussed was that we are inserting to the left of left. The previous case was if you insert in this in the subtree BL and you are increasing the height. So it would become actually the left. But what would happen if I insert to the left of F but to the right of B? The pattern this time would be this case, right? If I insert something in the right subtree of B, this is going to be completely different than the previous case that you insert to the left of B. This case is going to be the left-right imbalanced. Okay, this is completely different than when you are actually inserting to the left. This is going to be the second pattern, or which is in fact the symmetric of that is going to be the right-left. So whatever we are going to discuss for this pattern is going to be applied to this one, just the reverse of that. So now let's look at this case. If you are inserting to the right of B, this is going to be the else part. Remember this to if statement? It was checking that you are inserting to the left of F, you are increasing the height, and again here you will see that the height of B is going to be greater than the height of the right side of F, and it is the difference is going to be 2. But you are not inserting to BL, you are inserting to BR, which means that the item that you have inserted, you are inserting it to the right subtree, not to the left subtree. So this is going to exactly go to the else part. So this is how we check the imbalanced. Again, this part is going to end up to, if we look at the insertion tree, this is still this part. You are inserting to the left, right. This, the full if-else statement is coming here. I'm going to show you the full method at the end. But let's just actually discuss the, where it was here. Okay, so what I need to do this, I'm going to actually focus on these question marks here. What should I do if I have inserted to the left of F to the right of B, and I caused increase, I increased the height of the right subtree of B. You will see that this is an imbalance, and this is the imbalance in the form of a left subtree. This pattern is different than the previous pattern. So let me actually show you some general case of this one, that in all of these cases, again, F is 21, B is 6, and you are inserting to the left of F but to the right of B, to the left of F but to the right of B, to the left of F but to the right of B. All of these cases are the left-right pattern. Okay, so now we wanted to actually see that how we can fix this issue. The thing is, if I applied the previous method, rotating around a left child, if I rotate F around its left child, if I do this action, rotate F around B, I'm not going to fix the issue, because you can see that if I rotate F around B, the shape of the tree will look like this. F became, it's just like you put this one as the left subtree of B, and you make F to be the right subtree of F. The tree will look like this, and you are not fixing the imbalance. Still, the difference between the height of left subtree and the right subtree is 2. You just actually put the imbalance on the right side. Previously it was on the left side, you just put it on the right side, but you didn't fix it. So the previous action is not going to be enough. It's not going to fix the imbalance for me. To fix that, let me actually have a deeper look at this subtree BR. We inserted some node here in the BR, and that node increased the height. Okay, otherwise, if it doesn't actually increase the height here, for the BR, we are not going to have an imbalance. You should definitely increase the height to cause an imbalance. So now let's look at the right side, right subtree of B in, deeper. The thing is, in the right of B, we are going to have a node like D, and the value that you have inserted either should be inserted here or here. Doesn't matter which case. The thing is, I wanted to have access to D. I wanted to actually have a deeper look at the right side of D and know that what is the root of the right side of B. It doesn't matter if you have inserted the item here or here on the D dot L or D dot R, the right side of D or the left side of the R. They are going to be the same. The thing that I'm interested here is that this is the imbalance pattern for me, right? And the new node that should be the root of the whole subtree here is not B, but it should be D. Why? Because D is greater than B, but it is smaller than F. Remember, we always, if we are actually having an imbalanced case, either this one, remember it was 3 to 1, or this one, 3, 1, 2. The value, the node that should become the new root is the middle value, this one or this one. This is exactly the case for me. I need D to be the new root. Okay, this is the action that I need to do. I need to take D and make it the new root of the whole subtree. So F became the right of D, and I need to actually do an action like this, that F became the right side and B became the left side. I need to change the shape in this way. So after that, I need to actually figure out that what should I do with this subtree, with this subtree, and with these two subtrees as well. Okay, basically the thing is that the main two subtrees that needs to be detached and attached again is the subtrees of D. And now it will be actually simple that if I change the tree to be in this form, I don't need to change anything here, but the right subtree of B will be this one. I need to attach this part to somewhere, right? I need to attach this part somewhere. This is going to be the right subtree of B, and this part will be the left subtree of of F. And the reason is that all the values here are going to be smaller than F, but they are greater than D. So basically everything has been preserved. Everything are going to be on D sub R, are going to be on the right of D, but on the left of F. And everything here is going to be smaller than everything in this subtree are going to be smaller than B, so they are going to be assigned as, are going to be greater than B. So everything here are going to be greater than B, right? So they are going to be on the right of B, but still they are on the left of D. So this is exactly the action that I need to do. I need to make D the new root. This subtree will be assigned to the right subtree of B, and this subtree will be assigned to the left subtree of F. This is actually showing you the action. D became the new root. This part will be assigned to B, and this part will be assigned to F. Everything here is greater than B, and everything here is smaller than F. So we have preserved the tree. And now you can see that after fixing the tree, after actually making D to be the new root, the tree is going to be balanced. Here, the height here was h. The height here was h minus 1 plus, if you actually added a new node here, it's going to be at most h. So the difference, this one is going to be AVL tree, this one is going to be AVL, and this one is also AVL, right? All of them are going to be balanced. So now I'm going to show you how we are going to implement this algorithm. So whatever I explained to you was the approach that we are going to do. And the rest of it is going to be just a matter of implementation. You can do it in a different way. Just make sure that this is the algorithm. D is going to be the new root. Its previous left subtree will be the right subtree of B. Its previous right subtree will be the left subtree of F. And F will be its right subtree, B will be its left subtree. So how we are going to implement that, I'm going to just explain what your textbook did, which is in fact very nice in terms of the implementation. So this is the situation that we have. We are going to, in the first phase, I am going to rotate B, forget about F, I am going to rotate B around its right child, which is D. Okay, I'm going to rotate B around its right child. So it means that the shape of the tree will look like this. It's not going to fix the imbalance, but the nice thing about this action is that after rotating B around its right child, the shape of the tree is going to be exactly similar to what we had in the first pattern, right? If you think about it, now you can see that F is imbalanced, and the pattern that I have for the imbalance is exactly left-left, okay? So I can reuse the method that I have written for the left-left. So I need to do this phase. First, I'm going to rotate B around its right child. And then after this action, it will be very similar to the left-left pattern. And I'm going to fix it using that method that I have already implemented. So the first action to convert this tree to this one, this tree that I have, to this shape so that I can reuse the previous method, I'm going to call it rotate with right child. Okay, so and how we are going to rotate with right child, this is exactly the reverse form of rotate with left child. I have actually used this name B to make sure that you understand that what's going on. So it's just like you have B, right? And you wanted to rotate B around its right child, which is D. I have a new reference. This is not a new node. This is just a reference, okay? I created a new reference, which is going to be the right child of B. This is going to be D. I copied that there. Then I will update it B dot right to B. So B dot right will be D dot left. So this reference will be actually preserved here. Then the left of B will be, the left of D will be B. Okay, exactly similar to what we did in rotate with right child before we are done with rotation here. But just before leaving the method, I have to make sure that I'm updating the height as well. So the height of all the nodes, we need to make sure that we are maintaining the height of all the nodes properly. Otherwise, later on, we will get an issue. So update the height based on the the maximum of the left child, maximum of left child and right child plus 1, maximum of left child, right child plus 1. Okay, and at the end you just return the. If you think about this rotate with right child, this is exactly the symmetric of rotate with left child. This is very similar to that. So, and after that you can call rotate with left child around F. So this is the complete implementation of the imbalance for F, which covers the left-left imbalance here and the left-right imbalance. I have actually created a new method for this action, this double with left child, which was fixing this pattern of left-right, is in fact two phases, right? Rotate with right child, rotate B with right child. B is going to be the F dot left, right? And then rotate with left child, rotate F with left child, which is here the new left child of D is going to be D. So this is just the two phase. Instead of just writing it as two phase there, I have written a new method for that. And this is exactly the method that does the job. Two phases. First, rotate B around right child, then rotate F around the new left child, which is D. And that's it, we are done. The tree is balanced. What I explained to here was just a matter of implementation, okay? You could write it in a different way, but you can see that this is very nice. It looks very neat. Okay, again, remember this was the tree before inserting the node. After the inserting the node here, either here or here, doesn't matter which one, but inserting the node to the under D, to the subtree of D. After that, we had an imbalance, which was a left-right imbalance. After fixing it, we would get a tree like this, that either you have inserted E or C. In both cases, it doesn't matter, the shape of the tree will be again balanced. The F is going to be balanced, B is going to be balanced, D is also going to be balanced. If I'm going to show it to you over some example here, this was F, this was B, and this was D. Sorry, in fact, D was empty, so the node itself is going to be D. This was F, B, and this was D. F, B, and it was D. And you will see that in all these cases, we fixed the left-right pattern and we fixed it. Here I'm just emphasizing that the right-right imbalance can be fixed exactly similar to what we did for the left-left. Just the difference is that you in the left-left imbalance, you rotate around the left child. In the right-right imbalance, you rotate around the right child. So this one is going to be the new root. This one is going to be the new root. This part will be the left of 36. And 36 is going to be the left of 57. This is going to be the new tree. And the other pattern, right-left, is going to be exactly similar to the left-right. The difference is that it's just the symmetric of that. So if I'm going to show you the complete insertion method, you will see that this is just the modified version of the insertion method from the binary search tree. Compare this one to this was the original binary search tree, remember? And then here and here, we just checked for the imbalance and fixed it. Here, it is possible that you can have left imbalance, left imbalance, or left right imbalance. So both of these two are going to fix here, and here you might have right, maybe right, okay. So right imbalance or right left imbalance. So these two cases are going to be fixed here. These two cases are going to be fixed here. So now compare it to the modified version. These are exactly those two else if statement. You insert, and then you check that if it causes an imbalance. These are exactly checking that you have an imbalance, right? You have inserted to the left and the height of left became greater than the height of right by 2. The difference is 2. And then this case, this if statement, this case is exactly left pattern, and this is left right imbalance. And again here, this is going to be right, and this is going to be right, left. You see that you have inserted to the right of t, and the height of the right side became greater than the height of left, okay? And you have inserted to the right of right. X is greater than the right side. You have inserted to the right of the right. So that's why it became the pattern for the right. This one is the right, left. And we have fixed all of this. The rest of the method is exactly similar to what we had for the binary search tree. Here, there is no difference here, there is no difference here, and you return t as well. One more thing that we have added for the AVL tree is that just before you exit and return from the method, I am updating the height as well. You see that everywhere that there is a chance that the height of the node has been updated, just make sure that you update the height. Don't forget that, because we are going to maintain the height of all the nodes. Otherwise, later on, we cannot properly find the imbalance in our tree. So now you can actually think about the, all of these methods: rotate with left child, rotate with right child, and this double with left child or double with right child. This is the symmetric of this one, this is the symmetric of this one, right? The full implementation of all of those methods are here. Rotate with left child, rotate with right child, double with left child, which is basically just calling those two methods, or double with the right child, again calling those two methods. So I wanted to just discuss that. What is the time complexity of the insertion? Everything here is exactly similar to what we did for the insert in binary search tree. Remember, we discussed that the binary insert in binary search tree will be depending on the height O of h, right? You started from the root, searching for the correct position to insert the node. You insert it, you create a node, and you insert it. What I did in the AVL tree is that I just added a couple of if statements, right? Here I have added 2 if statement, if and else, and here again I have added 2 if and else statement, and this one as well. The cost of the last part is constant, right? Because I'm just checking 2 heights, getting the maximum of them plus 1. So definitely this is going to be constant. The if statement here and here are exactly the same cost. Let me actually check it. Although one of them will be in each function call, either this one will be executed or this one, but it doesn't matter. The cost of both of them are going to be constant. And the reason is that you can actually check the methods. These are the methods, right? Rotate with left child, the cost is constant. Rotate with right child, the cost is constant. You will see that in all of these cases, just a couple of assignments. These are just a couple of assignments. No loop, no recursive function calls, nothing. And these two methods, both of them are just calling two constant method. So definitely this one is going to be constant as well. This one is going to be constant as well. If I get back to the insertion, you will see that, okay, the total cost of finding and fixing the imbalance is going to be constant. Is going to be constant. So whatever was the cost of binary search tree will be the cost for the AVL tree as well. This is going to be theta of h. But what we know about the height in AVL tree is that the height in AVL tree will be theta of log of n. And so that's it. The time complexity of the insertion in AVL tree is going to be log of n. And this is exactly what we were looking for. So now let me just give you a couple of examples. It helps you to understand the problem better. I'm going to just solve a couple of examples here. There are more examples in the slides that I'm going to skip them in the video, but you can go through them on yourself, by yourself. So here, consider this tree. This, although it doesn't look very similar to the perfect or complete binary tree, but this is an AVL tree. Look at any of the nodes that you want. For example, this node here. This is AVL, right? Because the height of the right subtree is 2, the height of the left subtree is 3. The difference is 1, so this is AVL. If you look at this node, this is AVL as well. The height of the left subtree is 1, the height of the right subtree is 0, the difference is 1. Again, this is AVL because the height of the left subtree is 2, the height of the right subtree is 1, the difference is 1. And you can just, if you are not sure, just check all of the nodes. The height of this subtree, this node is also AVL balanced because the height of the left subtree is 1, right subtree is also 1, the difference is 0. This is AVL balanced, the height of left subtree is -1, right subtree is 0, the difference is going to be 1. This one is AVL balanced, the height of left subtree is 2, right subtree is 2, the difference is 0. This one is AVL balanced, this one is AVL balanced, right? The height of the left subtree is 3, this one is 4, the difference is 1. So this is an AVL tree. Now that we make sure that this is AVL tree, let's just insert a couple of items here. For example, first I'm going to insert 73. You start from the root. It is greater than the root, you go to the right. It is greater than the root here, you go to the right. It is smaller than this node here, you go to the left. Smaller than this node, you go to the left. Smaller than this node, you go to the left. And greater than 72, you go to the right. You create a node, insert it here. So now it's just like when you are in your function call, you are getting back. This node is balanced. This node is balanced. This node, it is not balanced, right? You have inserted to the, let me just clean here a little bit. You have inserted to the left of 81, to the left of 81, right? And the height on the left of 81 is 2, the height on the right side is 0. So this is not balanced anymore. 81 is not balanced and I have to fix the 81. What is the pattern? If you think about it, the pattern is exactly, I have inserted to the left of 81. This is left imbalance. If I'm going to fix it, the new root is going to be 75. 81 will be the right of 71, and 78 is going to be the left of 81, and this is the pattern of left. I fixed that, and this is going to be the new tree. Okay, compared with the previous case. This is the new root. This part will join to 81, and this is going to be the right of 75. The new tree. Now the tree is again AVL balanced, right? All of the nodes are going to be balanced as well. This is balanced, this is balanced, this is balanced, and this is balanced. And nothing else has been changed. So now let's insert another item like 77. So it is greater than the root, you go to the right. It is greater than the root here, you go to the right. It is smaller than this node, you go to the left. It is greater than this node, you go to the right. Smaller than this node, you go to the left. Greater than this node, you go to the smaller than this node, you go to the right, left. So do we have imbalanced? It's just like you in your function call, after you are done with the insert, you go back to this function call, right? Is this balanced? Yes. And then you go back to this one. Is this balanced? Yes. Then you go back to this node. Is this balanced? Yes, this is balanced. The right subtree, the height is 1, the left subtree is 1, the right subtree is 2, so this is still balanced. Then you go back. Is this balanced? No, this is not balanced because the height of the left subtree became 3. The height of the right subtree is 1. The difference is 2, so this is not balanced. I have to fix the imbalance at 87. What pattern is this? I am inserting to the left of 87, but to the right of that left. So this is going to be the second case, right? It is the left-right pattern. So what is going to be this is showing you the pattern here, right? What is going to be the new root? This item is going to be the new root. Okay, so 81 should be the new root of this subtree. I'm going to take 81 as the new root. This part will be joined to 75, and this part will be joined to 87. So this is going to be the result. This is just, I'm going to take this one as the new root. And this is the tree. This is exactly what happened. This part is joined as the left of 71, and this part is right of 75, and this part is joined as the left of 87. The new root of this subtree is 81. Let me show you another example. The tree is now balanced, right? Every part in the tree is balanced. Now I'm going to insert another item like 78. You start from the root. It's greater than that, you go to the right. It is greater than this node, you go to the right. It is smaller than this node, so you go to the left. It is greater than this node, you go to the right. It is smaller than this node to left, this node to the left. So then you create a node and you put it here. Then in your function calls, you come back and check for imbalance. In this node, is it balanced? Yes, this is balanced. Is this balanced? No, this is not balanced, right? Because the left subtree has height 1, the right subtree has height -1. The right subtree is empty, right? The height here is -1. So 78 is imbalanced. I have to fix it. What pattern is this? You can see that I have inserted to the left of 78. This is exactly the left pattern. And this is very simple. The new root node should be the middle item, right? Rotate around left. 77 is going to be the new root, and everything is going to be balanced. When you are actually looking at this node is balanced. This node is balanced. This node is balanced. This node is balanced. So the whole tree is balanced. Let's look at another example. I'm going to insert a new value like 80. You started from the root, it is greater than that, you go to the right. Greater than that, you go to the right. Smaller than this value, you go to the left. Greater than this, you go to the right. Greater than this, you go to the right. Greater than this, you go to the right. You came up here, it is empty, you create a node, you put 80 there, okay? And then in the function calls, you come back. This node is balanced. This node is balanced. How about this node? Is it balanced? Yes, this is balanced. The left subtree has height 1, the right subtree is 2, so this is still balanced. How about this node? The left subtree has height 3, the right subtree has height 2. Yes, this is also balanced. How about this node? The left subtree has height 2, the right subtree has height 4. So I found imbalanced here. The difference is 2. The node which is imbalanced is 69. I have to fix it. What pattern is this? If you look at it, you see that at 69, I have inserted to the right of it, and then to the left of that. So the pattern is going to be right, left. So what I need to do is to make sure that this is going to be the root node. So the new root of this subtree is going to be 75. So I'm going to fix that. This is the pattern, right, left. After you fixed it, this part will be assigned as the right of 69, and this part will be assigned as the left of 81, and this one became the root. This is going to be the new tree. Everything is going to be balanced now. Here everything is balanced, everything is balanced, this one is balanced, and this one is also balanced. So I'm going to stop here for the examples, but there are at least 3 or 4 examples here. You can actually check it out in the slides. Okay, so we are done with the examples for the insertion. Now I'm going to discuss about how we are going to remove a node from the a binary search tree which is AVL balanced. Here the idea is that I'm going to again just look at whatever I had in the remove method of binary search tree and just update it exactly like what we did for the insertion method. So after we are done with the remove, when we are actually coming back from the this is the remove method from the binary search tree, right? After you are done at the from the remove method, again we are going to check that when you are removing an item, it is possible that you make the tree unbalanced because you removed something from the tree, right? It is possible that you decrease the height of the tree, and because of that, it is possible that you cause an imbalance. So exactly similar to what we did for the insertion, we need to check for imbalance in when we are actually removing. But it is just a little bit more complicated than the insertion. This part is exactly similar to, so here, after you are done with the insertion, check for imbalance. Again, here, after you are done with the remove, check for imbalance. And not only that, you have to check for imbalance in remove min as well. Remember, this was the method remove in binary search tree. Let me actually just review the remove in binary search tree. In binary search tree, we had 3 different cases, right? Either you have just removing a leaf node, or you are removing a node with 1 child, or you are removing a node with 2 child. This was the case that you are removing a node with 2 child, that you get the minimum item from the right subtree and then copy it as the root and then remove the minimum item here. Okay, so this was actually the case there. So not only I need to check for the imbalance here and here, I have to check for the imbalance in the method remove min as well. So not only the method remove needs to be updated, you have to check for the imbalance in the method remove min here. But what you need to check for the to check for the imbalance is exactly the same if statements that we wrote for the inside the insertion. For example, if I am removing an item from the left part, it means that I am making the height of the, just think that, for example, this is T, you have a subtree here, you have a subtree here, right? Left subtree and right subtree. So if you are removing from the left subtree, it is possible that you make the height of the left subtree smaller than the height of the right subtree, right? So if you are removing from the left, the height of left, so T dot left, the height of that, this one, the height of, let me just write it as H. It's going to be smaller than, it is possible that it's became smaller than the height of T dot right. Okay, and because of that, if the difference between these two is 2, you have an imbalance. So what I need to check here is that if I'm removing from the left side, it is possible that if the height of T dot right minus height of T dot left let me just write it in different color, is equal to 2. This is the actually if statement that I need to. So I am checking for the imbalance here, and it is possible that I make the height of the left subtree smaller. So the imbalance that I have is going to be on the, I'm removing from left, so it may cause an imbalance on the right side. So you should look for imbalance here, okay? That either it can be a left imbalance or the right imbalance. Let me show it to you over an example. This is the best example. Okay, just assume that this is an AVL tree, right? If you look at it, this is an AVL tree. If you check any of these nodes, all of the nodes are balanced. Okay? Now I am going to remove a node like 1 from this tree. If you remove 1, you are first actually looking for it, right? You started from the root, you go to the left because it's a smaller. You are looking for 1. It is smaller than 8, it is smaller than this, it is smaller than this, you find it here. And then I'm going to remove this one. Remove this one, you return null to 2. So the you are removing 1 here, so the shape of the tree is going to be look like this. I am at 2, I'm checking for imbalance. Is 2 imbalanced? No, this is balanced. The left and right subtree, both of them are going to be, the height of them are 0, -1, so this is balanced. But how about 3? Is it imbalanced? You can see that I have removed from the left of 3, and it is possible that it caused imbalance on the right side. And yes, it caused imbalance because the height of the right subtree is 2, the height of the left subtree is 0, and I have imbalance. But what is the imbalance? The imbalance is in fact right. You see the idea? I have removed from the left, but I should look for the imbalance on the right because I decreased the height on the left side. So check for the imbalance on the right side. You find it, and how to fix it? Whenever you find the pattern, this is the right. You should exactly do the same as what we did in the insertion to fix it. So the whole idea here is that just find the imbalance. If when you find the pattern, any of those 4 cases that we have, left, right, right, left, just find it and just follow exactly what we did to fix it. The only difference is how we find the imbalance. Okay, so this part is going to be a right imbalance. You have to fix it. You rotate around the right child. 5 is going to be the new node, the new root node, and this is going to be the new tree. Now you will see one more difference between the insertion and deletion. Although this difference is not going to affect the implementation. Your implementation is just what I explained here to you, that find the imbalanced here, find the imbalanced here and here, very similar, and also actually inside the remove min, right? Find the imbalance and fix it. But in terms of, in practice, the difference between the deletion and insertion is that when you are fixing the insertion at the closest node, you will fix you fix the imbalance at the closest node, it will fix the imbalance everywhere else. But look at this example. After I find the imbalance and I fixed it, I have fixed the imbalance here, right? But still the tree has imbalanced. So if you check when you are actually coming back from this node, at this node, if you think about 8 is still imbalanced, unfortunately. So it is possible that you have imbalanced at all of the nodes starting from the root until you are removing the node. But it's not going to affect the time complexity. Still the time complexity is going to be theta of height of your tree, which is going to be log of n. Although you are fixing the imbalance at all of the nodes, you are fixing the imbalance here, you are fixing the imbalance here, and you are fixing the imbalance here. But still, the total cost is going to be theta of height, which we know that this is going to be theta of log of n. So let me just complete this example that we had. If you think about 8 unfortunately is imbalanced as well. The reason is that the left subtree, the height of left subtree is 2, the height of the right subtree is 4. I have imbalance at 8, and what is the pattern? The pattern is again right, left, right? The height of, you have an imbalance on the right side, on the left of that. So I need to fix this imbalance. The new node that should be the root is going to be the middle item, which is 11. You fixed it exactly. It is just rotate 16 around the left child and then rotate 8 around the right child. This is going to be the fixed form. So no, 11 is going to be fixed. If you think about the root, unfortunately root is still imbalanced. I have to fix it. You have removed from the left of it, the height of the left side is going to be 4, the height of the right side is going to be 6. The difference is 2. Yes, I do have imbalance here. And what is the pattern? It's going to be the right pattern. This is the pattern. I need to fix it. The new root node is going to be 34. And this is the tree after I'm done with fixing all the imbalances after the remove. So in terms of the implementation, this is very similar to what we did in the insertion. Just find the imbalance. Whenever you find the pattern, you can fix it exactly the way that we fixed the imbalance in the insertion. It is just a matter of find the pattern. Left, 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 right, 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 left. I have actually discussed that not only the remove method, remove min method should be updated as well. And never forget that you have to update the height of the nodes as well. Remember that we did it in the insertion method. Let me just show it to you again. That we check the height and update the height. You have to update the height in the remove method as well. Everywhere that you are changing the height of some node, you are fixing the imbalance, you have to update the height as well. I am going to just keep the final version of the remove in AVL Tree for your exercise. I'm not going to discuss it here. And yes, and that is the end of this video. We have checked that we can update our implementation for binary search tree and make it an AVL tree, a type of binary search tree which is balanced, and the time complex, the height of the node is going to be always log of n in terms of the number of nodes, which is n. So all the operations, find, remove, and insert, all of them are going to be done in O of log of n or theta of log of n. This is going to be a very efficient data structure that we can use to implement any sorted list, sorted container that we need. So please study the slides after you are done with listening to this video. We can, if you had any question, we can discuss it during the class.